You know how when you throw a ball up in the air, it goes up and then it comes back down because of gravity? And also how when you toss a coin, it lands on either heads or tails? Well, in the world of quantum physics, things don't work like that. Instead, the ball could go up and come back down with no force acting on it at all, just randomly disappearing and reappearing somewhere else. And the coin could land on heads and tails at the same time. Weird, right? Well, this weirdness isn't just some made-up fantasy. It's actually science. Scary, spooky action at a distance, dead and alive cats, particles that are bigger than planets. These aren't just ideas from science fiction movies, they're real phenomena predicted by quantum physics. So let's take a look at what quantum physics actually is and why it's so bizarre. Let's start with the basics. Everything in the universe is made of tiny particles. We're talking so small that you can't even see them with a microscope. These particles are called atoms, and everything you see around you is just a bunch of atoms put together in different ways. Like the chair you're sitting on. It's made of lots of tiny vibrating atoms glued together. And the air you breathe is mostly made of tiny oxygen and nitrogen atoms floating around. But here's where things get weird. When you zoom in on an atom, you'll find that it's not really there. Atoms are like ghosts. They only show up when you're looking for them. But before we go any further, we need to talk about light. Light is made of little packets of energy called photons. Photons are the smallest possible pieces of light. They're like Lego blocks that you can't break apart into anything smaller. Now, here's what happens when you try to look at an atom. Your eyes aren't able to detect atoms directly. Instead, you have to use photons of light to bounce off the atom and then get picked up by your eyes. But here's the thing, if you want to know exactly where the atom is, you need to use high-energy photons. High-energy photons are like fast-moving tennis balls. They're great for finding out where things are, but they're terrible at knocking things around because they're too rough. Low-energy photons are like slow-moving soccer balls. They won't tell you much about where the atom is, but they're much better at knocking it around. So here's the problem. If you want to find an atom, you need to use high-energy photons, but then you end up knocking the atom around so much that you can't tell where it is anymore. Or if you use low-energy photons so that you don't knock the atom around, you can't find out where it is. This means that atoms aren't really in one place until you measure them. Before you measure them, they're in a state of being in all places at once. This is called superposition. So that's kind of like the coin that lands on heads and tails at the same time. The coin is in a state of being both heads and tails before you look at it, and then it magically decides on one outcome when you do. But it gets even weirder. Sometimes particles actually disappear and reappear in other places. This is called tunneling. Imagine you are playing catch with a friend and you throw the ball to them, but it just vanishes before their glove can catch it. Then it reappears in their hands. Particles can do this through quantum tunneling. It's like when you're trying to find a job. You send out your resume and hope for the best. Even if you don't hear back from any companies, you never know where your resume might end up. It could be anywhere, just like a particle in superposition. So until someone eventually measures it, it's like the coin that lands on heads and tails at the same time. But it gets even weirder than that. Sometimes two particles become so linked together that they act like a single unit, even if they're separated by huge distances. This is called entanglement. Suppose you have two coins that are somehow linked together. If one lands on heads, the other automatically lands on tails, no matter how far apart they are. That's kind of like entanglement. But it's not just coins. It can happen with anything. For example, when you split a photon of light in two, the two halves become entangled. This means that if you know the properties of one half, you automatically know the properties of the other half, no matter how far away it is. Scientists notice that even though they are separated by distance, it's like the particles are communicating with each other instantly, but Einstein didn't like this idea at all. He thought that it was impossible for particles to be linked like that over long distances. He said that if you split a photon of light in two, you couldn't possibly know the properties of both particles without looking at them. But Einstein was wrong. Scientists have actually done experiments that prove spooky action at a distance is real. Here's how they did it. First, they split a photon of light into two halves. Then they sent each half to a different lab. In each lab, a scientist measured the properties of their photon, like its color or polarization. The scientists didn't know what these properties were, but they knew that if they had looked at the other photon, they would have known the property of their own photon without even measuring it. So they decided not to measure their photons. Instead, they just let the photons continue on their path. And guess what? The photons magically changed their properties to match up with each other, even though they had never interacted with each other. This proved that entanglement is real. So now we know that particles can be in multiple places at once, they can disappear and reappear in other places, and they can become linked together no matter how far apart they are. But that's not all. Particles can also act like waves, which makes even less sense. Waves are things like ripples in a pond, or sound waves, or light waves. They're like wiggles that move through space and time. Now, it is pretty easy to see how something like a rope or a jump rope can act like a wave. All you have to do is move it up and down. But how can a tiny hard particle act like a wave? It's like asking how can a rock act like a pebble? They're just totally different things. Well, it turns out that particles are kind of like rocks and pebbles. They have a dual nature. Sometimes they act like particles and sometimes they act like waves. It all depends on how you're looking at them. Here's a good rule of thumb. If you want to know where a particle is, you have to think of it as a particle. And if you want to know what a particle is doing, you have to think of it as a wave. We've covered a lot of weird stuff here, but let's take a moment to recap what we've learned. Quantum physics says that particles can be in multiple places at once. They can disappear and reappear in other places. They can become linked together no matter how far apart they are. And they can act like waves. This might seem strange, but it's actually true. Scientists have learned all this by doing experiments, and they've even used it to build new technologies like quantum computers and attempting quantum teleportation. Who knows what other crazy things we'll discover about quantum physics in the future? Maybe one day we'll be able to travel faster than the speed of light or teleport ourselves to different places. But even if we don't, we'll still have the satisfaction of knowing that the world is full of magic. Thanks for watching. If you like and subscribe, an angel in heaven will grow its wings.